All right, here we go, part two. We've got an equation, trig equation, and it's pretty nasty one. Looks like there's stuff all over the place. One thing I want to mention here, that side's not zero. So you know something's got to happen, right? I can't just cancel. I can't just cancel because if I divide by zero, everything goofs up. So how do I handle this one? Well, I'm going to move this to the other side and have another look at it. You might be tempted because you see a 2x there, maybe a substitution of some sort, an identity, right? Because we have those, left sides is cos 2x, and there's a bunch there. But as we'll see, we don't actually have to do that. This is a common factor one. Have a look. There's a common factor right there of sine x. If I take that and write it out front, now that I've got the one side equal to 0, I can split what's a fairly nasty equation up into two pieces. Sine x equals 0 and 2 cos 2x minus 1 equals 0. And I'm going to solve these both separately. How I solve that, there's a couple of different ways you could think of it. One way would be to think of this as rotation angle, right? We think of y as sine, so this is, where is the y coordinate equal to 0? Well, at that rotation angle, which is 0, this rotation angle, which is pi, and then this rotation angle, which is 2 pi. So, I see x is equal to 0, pi, and 2 pi, and so on. So if I wanted to state the general solutions, well, I could say it's x is 0 plus 2 pi n, or pi plus 2 pi n, and so on. But really, it's just every pi, right? So I can put these together into one general solution, which is just every pi n, right? Pi, 0, 2 pi, 3 pi, 4 pi, 5 pi, all will be solutions here. More interesting is this one. And I can see that once oh, by the way, over here, if it was your instinct to use the graph, sine x graph, absolutely that works as well, right? Where is this graph, y equals sine x equal to 0? Yeah, here, here, and here, and I can get the same solutions. So lots of different ways to get the same thing. And in this one, first of all, we need to sort of shuffle things around. The one's got to go to the other side and divide by 2. And then I've got one of these ones where there's a period change, right? I'm actually going to solve the simpler problem where theta is in the place of 2x. So here, I let theta equal 2x, and I'm going to solve this simple problem. Hopefully, you're recognizing this is a special angle. This has the related acute angle is, look it up on your chart. The chart is going to be on your formula sheet probably. It's pi over 3. And so, where is the cosine positive? I could think of it that way. Where's the cosine positive? It's in these two quadrants, right here and right here, where this is the related acute angle, pi over 3. And then I get my two solutions. Right, this is kind of theta 1, right, is pi over 3 plus 2 pi n. And I'm going to solve this in a second. But where's my second one? My second solution, theta 2. Theta 2 is, well, this is going to be the related acute angle pi over 3. So this is 2 pi subtract pi over 3. Plus 2 pi n, and I'll deal with that mess later. But that's straight from the rotation angles, right? So I could have, and it depends on how you do these things, I could have thought of this as the x-coordinate, right? The x-coordinate, x equals a half, is right there, and where is it across the unit circle? Well, there and there, and there are my two solutions, the same as if I use the cast rule. So dandy. Um, Now how do I actually solve this? Well, are those my solutions? No. Remember, I solved the simple problem. So I've got to substitute back. I got my 2x um, in the place of theta, and then I'm going to solve for x. Well, this one's not so bad. I just divide everything by 2. Right? Pi over 3 divided by 2. Watch your fractions, right? Flip and multiply, then this is pi over 6 divided by 2 is pi n, right? Because this gets divided by 2 here. And there's my general solution. There's a general solution there. And now I'm still working on this one over here. I'm going to call this one 2x2. How does this work? What's this? Well, some of you are getting pretty good that you can actually do this in your head, but I'm gonna do this in the margin over here. I need a common denominator. This is 6 pi over 3 minus pi over 3. This is 5 pi over 3 plus 2 pi n. Divide all this stuff by 2. I get 5 pi over 6 plus pi n. And then there's my general solution. So the general solutions are, from the first one, I've got pi n, solution set equals, and then I've got pi over 6 plus pi n, and then I've got 5 pi over 6 plus pi n. And then the principal solutions, remember the idea is we just go through and we pick out values of n until it gets bigger than 2 pi. Right? It gets bigger than 2 pi. So the solutions on the first spin, while n could be 0, 1, or 2 on that first solution, that goes with these ones here. That's those ones there. And then here I've got pi over 6. And then if n is 1, then n is 1. A little bit of fraction action there. 7 pi over 6. And that's from those ones, or those ones there. And then finally I get 5 pi over 6, and then add another 6 pi over 6 there is 11 pi over 6 are all the principal solutions, a whole bunch of them. That is a great trig equation question. It involves a lot. Would I ask you one that tough on the exam? Well, maybe not that tough. That had a little bit of everything in it, that one. Some identities. And I know you like to see some identities solved, but again, you can't see them all. You just need to practice, and it's not that big of a deal, right? But I'll do these ones, I'm hoping, fairly quickly here because I'm getting short of breath. So the right side here is secant x, 1 over cosine x. One of the strategies is to write everything in terms of sines and coses, and that's all we can do there, right? Maybe we'd want to multiply by a convenient form of 1 or something like that, but that looks like it's as good as we're going to get. Over here, as soon as I see tan x, and it's not a squared, if I saw a squared over here, I'd be tempted to think of the Pythagorean identities that I know you'll have on your formula sheet, but I'm thinking of that as a fraction. That's sine x over cos x plus cos x over 1 plus sine x. And somehow that's got to simplify to that. Well, I've got two fractions. Get a common denominator. That's what we need to do here. So big common denominator. Multiply this one by that denominator to get to the common denominator. Multiply this by cos x to get to the common denominator. And then I'm going to write it all over so you should be always sort of having a look over. Notice that my denominator's got a cos x, so somehow this has got to go. This is going to have to go somewhere, but I'm going to expand now. What do I see? Well, sine squared x plus cos squared x. That's equal to 1, isn't it? This thing here is equal to 1. That's the Pythagorean identity. So I'm going to write then sine x plus 1 over cos x times 1 plus sine x. Notice that I can't cancel the sine x's because they're terms, but that whole factor, that bracket, I can cancel, and when I divide out, that becomes 1. That's 1 over cos x, and we're done. Blah, 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 identity holds. Let's try another one. One more trig example identity to, and this one actually isn't so bad, even though it looks nasty. So the right side, and remember, there's more than one way to do these questions. Same as that, the trig equation that we did in example 2, there's more than one way. What am I seeing here? Well, this is one of those compound angle identities, right? And I know you had them memorized for the trig test, but they're going to be sitting on your formula sheet, so you should be able to just copy that right off of there. Cos y, and this is the sine one, isn't the one that's got the weird sign, it's minus there, so it's minus here. Cos x sine y. And it was A's and B's on your formula sheet probably, but can I cancel? Cancel, cancel? No, because of that minus sign. Remember, we can only cancel factors. We can't cancel terms. So how are we going to proceed? Well, I might be looking over here, right? Because tan x and tan y, maybe I'll write those as sines and coses, since the left side has only sines and coses. And right away, over cos y, having a look, on the bottom I got cos x, cos y, and when I get a common denominator here, is this going to work out? Absolutely. So here, common denominator is the only step I need. This gets multiplied up here, sine x cos y, minus, I wrote down the minus sign, running out of room. Can I squish this in? I hope so. Cos x sine y. And look, they're actually pretty nice to have a identity on the exam, because you know if you've got it, right? If you end up getting left side equals to right side and you haven't done anything goofy, it's a really nice feeling. All right, that's it for trig. Lastly is the unit on logs. We're not going to have any review videos on the Unit 5 modeling, because, geez, you probably just did it. You just finished it. Maybe you got your test back today or something like that. Something like that. So next video will be our last video on logs.